In this video, we're given measurements of the diameter and the height of an aluminum cylinder. We're told that we took these measurements with a set of calipers. Each of these measurements is given a plus or minus uncertainty on it of 0.002 centimeters, which is the actual uncertainty on the calipers I have in the lab. And what we're paying close attention to in this problem is using the propagation of errors formulas to properly get the uncertainty in the volume of this sample. So we begin in part A by finding the volume of the sample in cubic centimeters. And the volume of a cylinder is just the area of the base multiplied by the height. And one important point in this problem is that to deal with uncertainty properly, we need to state the volume formula in terms of those things that were directly measured. So instead of writing a radius there, I'm going to write diameter divided by 2. And when I square the diameter over 2, I get a factor of 1/4, and I'll just pull that out in front. So we're using the formula 1/4 pi diameter squared times the height. So we just have to plug the numbers in now, and it's 1/4 pi. The diameter is 3.226. The height, 7.500. And I'm going to keep a lot of extra precision until we get to part B. Our volume comes out to 61.303 cubic centimeters. In part B, we're asked to use the propagation of errors formula to get the uncertainty in the volume. And then what isn't stated in the instructions here is that when we get that uncertainty, our convention is to round the uncertainty to one significant digit and then round off the original volume measurement to that same place value. So the volume is a product of a power of one measured quantity, that's the diameter, and then another measured quantity, that's the height. So the propagation of errors formula that we're going to use looks like this. I say the relative uncertainty in V, in other words, delta V over V, is the square root of 2 times delta D over D, and the 2 is there because it was squared in the volume formula, and then I have to square that term, plus a delta H over H squared inside that square root. So we plug in the numbers. Our uncertainty in the diameter was 0.002, the diameter itself, 3.226, the uncertainty in the height, 0.002, the height itself, 7.500, and I get 0.00127. Now this is the relative uncertainty in the volume. In other words, you think of it as a percent uncertainty, so it's about a 1/10 of 1%. To get the actual uncertainty in the volume, we need to multiply both sides by that V that's in the denominator. So delta V is 0.00127 multiplied by my volume itself, which was 61.303 cubic centimeters. And this gives me an uncertainty of 0.078 cubic centimeters. As promised, I'm going to round this to one significant digit, so my uncertainty is 0.08 cubic centimeters. And then I'm going to round my original volume to that same decimal place addressed by the uncertainty, in other words, the hundredths place. Because there's no reason to include extra digits in my volume measurement if I have uncertainty in the hundredths place, the thousandths place becomes irrelevant. So we state our final volume like this. V is equal to 61.30 plus or minus 0.08 cubic centimeters.